Thank you all for postponing your lunch hour to be here with me. Thank the organizers for giving me a chance to speak. I'm going to talk about Picard groups. That's a very general idea. Let's start there. We already had them this morning in another context. So you can define it very generally. If you have some symmetric monoidal scatter order with some hypotheses, then the Picard group of C is equal to the isomorphism class of the invertible block. Things that, X such that X tends to Y such that X tends to Y is isomorphic. So, of course, I need some hypotheses to make sure this is a set, but other than that, it just becomes okay. I don't quite know where this originated, but you certainly encountered it in your first algebraic geometry class. And the theorem, for example, that the Picard group of invertible sheaves on an elliptic curve is isomorphic to the elliptic curve itself is still one of the most kind of amazing theorem that tells us a lot. It's a very sensitive invariant of the category itself. I'm not particularly interested in that one. Well, of course I am. But let me rip off the mask right away. We're interested in categories like, so the ample examples I'm going to talk about today are C is going to be equal to stable homotopy category. This is the stable homotopy. Localized at some homology theory. Example 0 is, of course, C is equal to the stable homotopy category itself. And I really mean host class. Let's talk about that in a second. And then pick here is simply isomorphic to the integers generated by S1. You might be able to guess that, but the proof is actually rather subtle. It's due to, I think it's due to Pham, and Stojanoska. If you could show that an invertible spectrum is connected, that vanishing homotopy groups below a certain degree, this would be easy, but that's not obvious, and you have to prove that. But the big example today is I want to talk about the case where E is equal to model K. So this is Hopkins' Picard group. In theory, and then I'm just going to write pick N for pick. I'll remind you in a second what Moronic K theory is. This was introduced by Hopkins in the late 80s. It's part of the whole chromatic point of view of homotopy theory that breaks things down in various ways in this. So what is Moronic K theory? So Kn star, I'm going to take a slightly different version than Nick did. I want to take a true periodic version where I0 is a field of, I joined the P to the N minus first root of unity to P. Nick contained this version. That inclusion is an ATOL extension, so it doesn't change the homotopy theory at all. This is complex-oriented cohomology theory. And so, the formal group law, is Hogan. It's typical, it's fashionable to write N instead of H, or H instead of N, for this some sort of height. My N's My H is same letter. So.
For everybody, yeah. Nobody understood it.
That's right. Let me save some space here. When people draw the, there's an N and a P here. There's an N and a prime. When people draw this, so N is equal to the height, and P is equal to the prime. And then there's this sort of whole Balmer spectra game here you draw. You start drawing dots at, let's start with one. I'm going to draw this line here. It's a line that goes. That's 4. And it's equal to P minus 1. So at each one of these things, you have a height and a. You've got at each prime, you have a height that goes with the n. And we tend to draw some picture that goes like this, but these dots don't have equal dignity. So out here is some sort of algebraic zone. I'll make this more precise in a minute. It gets more algebraic the more you go that direction. This might be called the Ravenel line, because that's the line where he used to disprove the existence of covariant variant one elements at large primes. This line, we might call that the one that goes through 2 here. Let's call that the Mahowald line. And I think we have some sort of conceptual understanding was going on here, but in here we have no idea. If this were a medieval map, this is where the sea would be with the serpent. Unknown territory. We have no idea what's going on. And then, of course, if this were a medieval map, we'd have to have like God up there someplace. Who's God? And God's other name is Hopkins. So we should definitely do it. So I'm going to go on this. I'm going to go around this corner. That's what we do. Now, going out here. There's another homology theory, E star. This is Murata E theory. It's really a functor of the ground field and the formal group law. Its coefficients are some bit vectors. This is all on degree 0. 0, and again, it's a 2-periodic theory. And that's the thing that rules our world on the Murata E theory. There's a group here, which I'm going to call GM. It doesn't really matter what it is. It's the automorphism for this talk. It matters a lot what it is, but the content of this talk, it's some giant profinite group. It's the automorphisms of this formal group law, and there's the Galois law. And this group acts on this thing. In fact, it acts on the spectrum. That's the celebrated Hopkins-Miller theorem. Devinet's all these people work on this. Okay. And I'm going to use this guy to control my story. Okay. Let's put that back up. Why is that a useful thing to do? So the initial theorem here, this is due to Hovey and Sadowski, is that X is an element of pick n. So I have some Kn local invertible spectrum if and only if E star of X is free of rank 1 as an invertible, as a E star. Now the warning is that this is not the E star homology of X. This is actually pi star LKN. That's a kind of completion process. You should regard that as a good thing rather than a bad thing. The p-adic extents of themselves over the integers are not something you ever want to think about. It's the same kind of thing. You complete that and you get something else. So, all right. So in particular, what's the consequence of this? I can define pick 0 n contained in pick n. This is equal to the set of x, so that E star of x is an even degree. It's an index 2 subgroup. And we get a short exact sequence. So we take pick n0. We'll go to F1 of Gn coefficients in E0 cross. That's this giant power series ring. Simply by taking x and going to E0 of x, and regard that as an invertible. So this is free of rank 1 over E0. Now, it's free of rank 1 over E0, but it might have a different action of the group Gn. Okay? So if you choose a generator, you act on the generator, you have some function times the generator, that's a cocycle. Okay? And that gives you something neutral. And I'm going to call the kernel is going to, yeah, I'm going to call it K. So there might be a kernel. All right. And here's some theorems to make this precise. So the theorem 1, this is again HMS. Let's call this map something. Epsilon. So theorem 1 is that if 2p minus 2 is bigger than n squared, then epsilon, then kappa n is equal to 0. Epsilon is an injection. And then a more refined version of this, which I think Beaudry wrote down. If 2p is still larger than squared plus n, then epsilon is a right. So in this sense, out here I get something algebraic. This topological object becomes an algebraic calculation. That's impossibly difficult calculation.
So this bond was recently improved by Drew.
Okay, Drew.
Right?
So here.
So now it's 2p minus 2 larger than n squared as well.
Oh, so he can eliminate that.
Yes.
Okay. So that's I didn't know that. Thank you. He's not here because he knows all the answers. All right. And so that's the next thing I want to do is tell you about some elements in these groups. That's the wrong thing.
Your racist snake will just appear somewhere else, you know.
Each time I gave a talk in Germany, which was a while ago, and Helmut Kohl was only in his second term. And you could, from my apartment, you could walk to the East German border. I gave this talk, and at the end, instead of clapping, they knocked on the table. And I said, holy crap, I didn't think it was that bad. But that's it.
By the way, Drew is letting us know that he's downstairs.
Okay. He's been busted, is that the let's see. Let's talk about some elements. Well, first of all, let's put it in pick 0. So to be in even degrees, I can look at LKN of S2. That's not, that's the unit, but LKN of S2. The 1 cocycle, so that corresponds to some 1 cocycle. Phi, which goes from this group Gn into E0 cross. Well, phi of G, that's just equal to G prime of 0. Where, remember with G of X, G is equal to G of X is an element of the automorphisms of the formal group law, or FPDN, which is a sub-object in the power series of X. The ideal generator of X. So I just take the leading coefficient. That's a very simple cocycle. Far more subtle is the determinant. This Sn, this group here, that's contained in the endomorphisms of this object. And this is a rank, this is division algebra, or the groups of units in a ring of units in a division algebra. It's rank n over the bit vectors. So that's p to the n. So in particular, I get a map from Sn into GLN W, and I can take the determinant, which nominally lands here, but in fact it lands inside the p-adics. And I'm going to call that the determinant. And I can extend that over, Gn. So that gives me an actual homomorphism. Okay, it's a homomorphism from here to the p-adics. And in fact, I'm going to confuse that. And that's, of course, contained in here. Okay, so that's a cocycle, and I think that determines an element of H1. And there is a determinant sphere. There's a sphere. S det, an element of the Picard group with E0 of S det or E star of S det is equal to E star of the sphere, the trivial thing, tensor over the p-adics, completed tensor product over just action by the determinant. Where the GNX diagonally, it acts on this normally, and there it acts through this map. So let's see, the existence of S det at p bigger than 2, Hans Werner and I wrote down an example, Peterson wrote down an example, Eric Peterson. And then for p equals for all primes, p bigger than 2, we wrote down something, I'm going to use acronyms. So this is Barthel, Beaudry, Goerss, and Stojanoska. At p equals 2, it's much more subtle. There's choices. We made a particular choice. All right. So that gives another example. Let's see. And it's probably working well. These generate a lot of groups sometimes. I have some nice, let's write down 3. Let's see. What happens if n is equal to 1? Then G1 is just equal to the units in the p-adics, and E0 is also equal to the p-adics. And you're calculating H1 of ZP cross, the coefficients in ZP cross. Okay? If P is large, meaning not 2, that's just a copy of the P-address. Bigger than 2. And the generator here, you can take it to be S2. You can take it to be the determinant, turns out to be the same thing. But the prime 2, it's much more interesting. It's larger. And the determinant, or the 2-sphere, generates some copy here, and then the question is, what are the other generators? And I'm going to get back to that. There's more going on. So that's back on the Mahola line. All right.
Oh, you sure you're not missing some P minus and 4?
It's probably a cross. It's still general. As a topological group, the units of P's allow primes of a single generator. Piece of paper and a squeegee and that. Incidentally, I wrote down this map from the topological to the algebraic to the H1. That was continuous cohomology, and the target there has a topology, and so does the source. There is a topology on this topological Picard group, which comes out of the nilpotence theorem. That's written down in great detail in Hovey and Strickland's memoir, but of course it goes right back to Hopkins as a working discussion. He understood then. And you're seeing the topology here, these are the answers. All right. There's another object that I should tell you about, and that's IN, which is the Gross-Hopkins dual of the sphere. So, I'm not going to define it or tell you much about it, but if X is a type N spectrum, X is finite type N, which means it's lower Murata K theories are equal to 0, then I can write down the following formula. If I take the function spectrum IN, this is equal to the Pontryagin dual of the homotopy groups of, I guess I don't think they'll keep it. So in that sense, it's part of this duality, algebraic duality. And then Gross and Hopkins proved that what E star of IN is isomorphic to E star of SN squared minus N, twisted by this determinant again. Okay. So again, I do this twisting, I guess I use parentheses. All right. So in particular, as an element of, this is an element of this pick n0, this is always an even number, okay? So IN is equal to Sn squared minus N smash S depth smash P, where P is in this algebra, P is in Kn. So this is equal to the set of X such that E star X is isomorphic to E star that's not with a Gn, has Gn models. It's indistinguishable to E star. All right. With me so far? Okay. I would expect you're with me. Okay, so let's talk about Kn. How do you produce elements in Kn? So that's the difference between, remember my chart, I had this, if I walk this way, I got more and more algebraic. This is walking this way, going north, okay? If I want to talk about the p-local homotopy type of anything, I have to go north. Going out is, so let's go north. So there's basically three ways. Let's talk about one of them. And one of them is here, okay? So find an x. I want to make an observation. In is invertible. This Gross-Hopkins thingy is invertible, and that tells me that in of x, which is equal to f of x into in, that's equal to x into, I can just take its categorical dual, smash in. All right, and let's call this thing dn. That's some sort of Spanier-Whitehead duality of x. So in strategy one is to find x so that I want to use this formula so that C, in of x does not equal Sn squared minus n S smash S det smash dn of x. And then star would say P has to be non-trivial. Star implies P does not equal the sphere. Well, you can do this in lots of fun cases. So let's give some cases. So the basic example, going all the way back to HMS, is that if n is equal to P1 equals 2, then in of KO, real K theory, is equal to suspension 5 KO. And dn of KO is equal to suspension KO. And this guy here, Sn squared minus S det, is exactly equal to S2, at least for some choice of S det. Okay, so they have to be different. So P is not, so there has to be something. Okay. This is not, 3 is not 5. And it turns out that this is a basic example. I'm going to write down a whole bunch of examples in a second. At this point, we're starting to use some of the deeper structure of this spectrum E. So far, I've only written down that it's some sort of homotopy action of this group G. And in fact, the group Gn, but the group Gn actually acts. And it acts in some sense continuously due to the work of Devenitz and Hopkins and others. So in particular, if I have a finite subgroup of this group Gn, I can take the ordinary homotopy fixed points. I'm allowed to do that. And so in this particular example, E, n equals 1, E is actually P-complete K theory, and C2 is plus or minus 1, so now P equals 2 is contained in Z2 cross, and that EHC2 is equal to KO, P-complete. And then we have theorems like the same strategy works at n equals 2 equals p. That's a Bobkova. I'm not doing this in historical order. N equals 2 and p equals 3. That's Barron's. And then on the whole line, on the Ravenel line, n equals p minus 1, it also works there. That's, let's see, Beaudry, Goerss, Hopkins, and Stojanoska. Do I have that right? That's the, so in historical order, this was 1, well, this was 0, this is 1. In fact, we were looking for some sort of conceptual explanation for this. In all of those cases, we calculate IN of EHCF and DN of EHF, where F contained in GN is some sort of maximal finite subgroup. Containing a p torsion. It's the p torsion that causes all the trouble. In fact, they have finite subgroups of p torsion. Okay, these things are closely related to the Hopkins-Miller theorem of topological modular forms. It all gets tied up. All right, so that produces examples. What about 2? Here's another method. Remember, we have this determinant from, well, let's put it this way. We have this determinant Gn into Zp cross. And I can keep going. I can mod out by the finite subgroup. Okay, so that's isomorphic copy to Px. And I'm going to let the Gn1, that's equal to the kernel of this map. And it's really this map. So it's, you're off by 1 generator, okay? Now, there is, because this is just basically a copy of the integers, it's a fiber sequence. HG N1, psi minus 1, EHG N1, like so, okay? This is a generalization of the, I don't know who is due it. You have atom summit, or K, K, and KO, for example, which is an old theorem due to, or KO, KO, and the LK1 local sphere, which is an old theorem of Robin's. So that's the trivial element of the Picard group. But if I have an X, which is an element of the kernel of the Greiwitz map, E0, like so, then I can twist this. I can replace the 1 by the 1 plus x, okay? Then we can form, let's call it just x of x. Maybe 1 plus x is better. This is in this fiber sequence, EHG and 1 and psi of 1 plus x now. Now that doesn't change what happens on homology, because this was in the kernel of the Greiwitz map, okay? So that gives you a theorem. I wrote it down, but it's new to lots of people, I think. That gives you a map from this kernel to this K star. So the assignment, so I've got this x goes to x of x. Where does that go? Well, it's really 1 plus this kernel. Let me call this thing k. So it's a map from 1 plus k to that actually it goes to into k n, and in fact it induces an injection. There's an action of the there's this residual ZPX on this, and this gives a map here, and that's actually the injection. In fact, it's an injection on a particular subgroup. It's the ones when you smash it with a ZHG21 that become trivial. Now, that means you have to calculate pi 0 of this thing to get any, and I'm not tough enough for that. That's why I have co-authors. Okay. I'll give you examples in a minute. All right. There's one other method, and that's the other thing in the title. Suppose I have a finite subgroup, and that is finite, and B is a real representation, virtual real representation. Everybody's favorite.
Is F equal to G?
What's that?
Is F equal to G?
F is equal to G. That's the least to memorize. All right, then I can take E, I can smash it with 1 point compactification. GNX diagonally, I can take its homotopy fixed points, and I'm going to call that something. That's J of V, and maybe I should put an F on it because it's going to depend on that. All right. So what does this give me? This is very, so it's a theorem actually, which maybe, so this is from Beaudry, Goerss, Henn, and Hopkins. Who am I thinking of here? I'm thinking of Barthel, Beaudry, Goerss, and Stojanoska. We wrote down an argument that that thing is that J of V is actually an element of the Picard group. And if V is a virtual dimension 0, and Fx trivially on H0 of SV, which is a copy of the integers. So unless you have a Z mod and 2 floating around, it's going to happen. Then J of V is actually an element of counts. So that's another way to produce all sorts of fun elements. One issue here is that for you fans of GN, this is only going to be interesting if F has P torsion, okay? And there aren't a whole lot of homomorphisms from this thing to F with P torsion unless P is equal to 2. And then there's tons. All right. With me so far? Now I'm going to give you the theorems, okay, or a list of examples, okay? You ready?
Yes!
He's ready to put the rest in the Okay. Examples. So let's start with the, this is the Hopkins-Mulholland-Sadowski example. There is a short exact sequence. Let's see, it's 0, It's K1, this is P equals 1, N is equal to 2. Well, you know. I had a terrible time with left and right. My whole life. It causes all sorts of family fights. You know, turn left and left. Anyway, pick 1, I guess I was calling it. And into this H1, Z2 cross Z2. This turns out to be onto, which wasn't obvious. This is isomorphic to Z mod 2. This is the thing in the middle. And this we wrote down earlier was Z2 cross. Now, this Z mod 2 you can get by using any of the methods 1, 2, and 3. All 3 of those will produce the Z mod 2. Inside of here, you've got the sphere. You've got the thing corresponding to LK1 of S naught. But that only gives 1 generator. And where did the other 2 generators come from? They come from, the other 2 generators come from, use J of sigma minus 1, where sigma is the sign representation. And you use, these are and you use the various homomorphisms from Z2 cross down to Z2. There's in fact quite a few such homomorphisms, right?
Well, this LK1 is 0, should that be S1?
S2. And this should be pick 0. Otherwise I have to put a, all right? Now the fact that this, I didn't say it, but this thing is a homomorphism, and the fact that I can construct this element can be constructed as J of 2 sigma minus 2, that means that there has to be an extension here. It's not split, okay? There's actually a Z mod 4. Okay, so that's the first one. I have 2 more examples.
Increasing levels of difficulty.
I began this, Quantenberg and Henn and I have been working together for 20 years and all sorts of stuff. This gives me an excuse to go drink beer with Hans Werner. In various exotic locales like Pham. We worked out various things at the prime 3, including the Picard group and the exact homotopy type of the Gross-Hopkins dual of the sphere, a bunch of other stuff. And then, I don't know, maybe it took 60 pages of work. And then since then, we've been working on the prime 2 with like 75 co-authors and like huge groups of people. And it's like 200 pages so far. So there's some exponential leap of difficulty at the prime 2. And that's where I'm going to end. Okay. But let's now do the case.
There's nothing about the prime 1 then, you know.
The prime 1. Like this, the first talk today was extremely elegant, and one of the reasons it was elegant is I kept getting used to doing and stuff.
It kept in quiet.
What happens if n equals 2 and p equals 3? In fact, you've got K2 into this pick 2, 0 into this H1 of G 2 E0 cross into 0, and this is generated by what comes from LK2 of S2 and S def. So they're separate in this case, and they topologically generate this group. It's roughly 2 copies of it, yeah, so it's not quite rough. Okay, this turns out to be split. This is, let's do the Karamanov, actually, the calculation. And then this was GHMR, so Goerss, Henn, Mahol, Rusk. The other Goerss, Henn, Mahol, Rusk. Not the resolution split, but the other one. This is Z3 cross Z3. And one of these is method 1, and the other one is method 2. The one where you twist the top. And this was, even Barron's noticed that this one had to be here, and then that's a calculation of the homotopy groups of this pi 0 of the HG21. That turns out to be cyclic of order 3. It's a very simple thing. There we did use the first GHMR. All right, so then there's no funny extension in this case, partly because there's no J. There's no real interesting homomorphisms from G2 to Z-homotopy. Now we come to the punchline. What happens if n equals 2 is P? Now,
Well, you can get, I think you can get it with method 3. I think there are.
I stand corrected.
Yeah.
As somebody said in an earlier talk, if I'm standing here, I'll believe it.
Yeah.
So what's the correction?
The assertion of the existence of an interesting homomorphism from G2 to some finite. All right, perhaps that's correct. Anyway, our original construction was definitely 2. And so let's see. First of all, I've got the same sequence. Pick 2, 0, H1 of G2, E0 cross. So this has been computed, although it's in some secret document that he won't release by Henn. You don't even show it to me, so that's a little worried. But
Give it more beer,
we're not sure. Is it onto? We don't know that it's onto. We know that it's onto a subgroup of index 2. Okay, and there's this extra Z mod 2, much as there was in this case up here. There's these extra Z2s floating around. You can't quite nail that. This guy. So this is like every possible person that could ever be a referee on this paper is on the co-op list. So, Beaudry, Bobkova, help me out here on
Goodness.
is that maybe Mark Barron's?
What does it refer?
So Mark Barron's is not on there. You should quickly join the list, otherwise he's going to be the referee. Kappa 2 is equal to Z mod 8 cross Z mod 8. Now, for aficionados of this game, that's the same thing as Z2. Just, it's really new, right? Pi 3 of S2. That's not okay. But that's not why I'm going to break that up. Z2 squared cross Z2. I want to break it up this way. This is method 1. This is method 2. And this is method 3. We need all 3 of them. They don't overlap. They start to pull apart. All right. And that's, there's some conjectures here, perhaps, that maybe you could get all of them this way, but I don't believe that. We're just, n is so small here, that, the principle of maximum happiness doesn't really keep. All right, so I'm going to talk about this one to kill the rest of the hour. Let me. All right. So that uses this J construction, not just in a fun way. It uses it really. Okay. So I have a homomorphism, which I'm going to call X in violation of the notation in our paper, which goes from G2, I can take the determinant, goes to Z2 cross. And then I want to mod out by the torsion free part. This is an example of P turning into 4. So that's a cyclic group of order 2. All right, and now so that's my X, and I want to look at Jx of 2 sigma minus 2. Sigma known with R of C2 is the sum. And that's going to be my generator. Well, not quite, but we'll let that X was possible. So I'm just going to call that J. Now, what is that? J of 2 sigma minus 2, that's equal to EHS 2 sigma HG2. But that's the same thing as EHSG, call it SG2, smash S2 sigma. I'll write it this way. This is E. HC2, where that's the kernel. SG2 is equal to kernel X. And so I get a map from just this 2 sigma minus 2 into HC2. Because I can write this as I can just put an S naught on here and include it in there. The action of this group is this is a classical object. Back in the late 1970s, early 1980s, when we were all sort of studying the Segal Conjecture, we spent a lot of time thinking about things like that. Okay? So let me tell you a little bit about that thing. Let's just take a general K, and let's look at SK sigma HC2. Well, what is that? Well, by definition, it's the C2 function spectrum from, if you like, the suspension spectrum of the infinite sphere with the antipodal action into SK sigma. That's, if you like, that's even the definition, okay? Well, that's the homotopy inverse limit of, again, C2. When we drop the sigma infinities, I can take the homotopy inverse limit over M over the n spheres of SK sigma. But this is invertible. I can put this thing on this side. Now it's a spectrum, so I won't worry too much about the base point into S naught. And then I can just mod out by the C2, okay? There's a gap there. It's just the Spanier-Whitehead dual of this thing. Homotopy orbits into S. And that, you know what that is? That's equal to a truncated projective space. There's a suspension RP minus I hope I have the numbers right. K minus 1. What is that? Well, if these things are positive, RPS is contingent on RP infinity is the end skeleton. And then maybe RPS minus RP2, RPT, that's equal to RPT minus 1. That's RPST. If they're not positive, then it's the Thom spectrum of some appropriate bundle of projectors. And the point is this is a very classical object. Oops, battery broke.
So gotten a particularly bad one just to display everyone in homologous inferior. You know?
Yeah. So let's look at my picture up here. I have S. That's 2 sigma minus 2. This minus 2 is going to introduce a shift, HC2, into this J of 2 sigma minus 2. And I have these maps from RP. How did it end up? Suspension minus 1, 1, 1 minus M. And a theorem, so this is Devon-S Hopkins vanishing, implies there is an M for their suspectors. So in fact, you don't need to go to this, you can deal with this actual God, right? This actual finite significant complex. Now let's see, what is RP suspension minus 1, 1, M minus 1? What does that look like? I'm going to draw a cell diagram. So this is going to look like the cohomology of this thing. So you have a class in degree 0. That's the top class. The top class from here, and I shifted it down 1. And then there's one class down for a while. Okay, I want to go get far enough so I can tell a joke. Okay? And then these are connected by schema operation. Okay, so that's a square 1. That's a schema operation. And then there's a square 2, and that's the only one that matters. There's others too, but I won't tell you what they are. And how many people in the room know that this immediately implies that in the Adams Novikov spectral sequence, HS, GN, ET, J of 2 sigma minus 2, D3 of iota is equal to Y eta, where Y is the box line. And that shows that this is a non-trivial class. Now, how many people know this? Nobody, right? It's the 8 is the connected map.
That's like the 1 cell. Doesn't it start with 1 and goes down?
The top cell is shifted down to degree 0.
That's a minus 1.
Yeah, it's a minus. Well, this is a minus. So, and this implies, so I'm not going to go into this. It's not true. So the joke is, if you spent your 20s with Mark Maholo, this will be obvious. All right, that's enough for today. Thanks for listening.